Hey, PCalc students, just wanted to give you a little review video. I've been getting several questions regarding the difference between intermediate value theorem and the mean value theorem, and when do you apply each, and it can be a little bit confusing. So I wanted to make this as simple as possible. I'm going to use a little slang in here, but I want to contrast them. So to the left here, I have the intermediate value theorem, and to the right, I have the mean value theorem. Mean value theorem is based on calculus and derivatives. Intermediate value theorem is actually algebraic and is based more in pre-calculus, and we use this a little bit differently. Let's just jump in and see, and let me show you. Oftentimes also we use the intermediate value theorem to prove zeros exist. Let me sketch a graph, and then we will explain. Well, let's draw a graph that just gives us that situation. So I'm going to draw two eventually, but I'm just going to draw one up here. And so here is the first one. I'm going to draw a function that is continuous over the interval, and this will be our x-axis here, and this is our y. And I'm very intentionally here going to make my interval, although my function is continuous, I intentionally here want the function to cross the x-axis in between these. And so there is my function. It is continuous on the closed interval, and here is my f of a value, and down here is my f of b value. Bring this all the way over, and I would say f of b. So I'm going to do this twice here because of the pre-calculus application and the calculus. So I'll make this just a tad longer so it's easier to read here. All right, so if a function is continuous on the closed interval a to b, then if, I'm going to continue with my if, and if f of a, okay, so there's my y value, f of a is greater than 0, and f of b is less than 0. So I have f of a is positive, and f of b is negative. Here's my then statement. So the reason I didn't conclude that is because the rest of this and statement is a little bit different when you apply it in calc class. So if a function is continuous on closed interval a to b, and if f of a is positive and f of b is negative, here's my then statement. Then there exists a 0. Which you can see right there. There's my 0. There exists a 0 on the interval a is less than x is less than b. So the 0 has to be in the x interval, a to b, if a is positive, f and b is negative. Now this is fairly intuitive, and you look at that and you go, well, yeah, that's got to make sense. You give me a y value, as long as my function's continuous. If I don't have continuity, it could be a whole other deal. As long as you're continuous, because it'd be very possible to have this situation, and if you disregard continuity, it wouldn't be true. So just to give you a quick example, I don't want to belabor the point over here, but I'll just draw an example. What if you had a function that looked like this? What if we had maybe something with a vertical asymptote and a slant asymptote, and your function was doing this, and you probably remember these from pre-calculus. What if this was your function? And so here would be your a value, and here was your b value. Well, continuity is really important, because if we went up to here and we said, yep, there's our f of a value, and down here would be our f of b, make our y-axis a little bit longer there. There's our f of b, there was our x-axis and y. You could look at this and you could say, well, f of a is positive, and f of b is negative, therefore 0 exists. Well, there's no 0. Because I wasn't a continuous function. So continuity has to exist in order for this to hold. Okay, so just a side note there. So here we are, we have our continuous function on the interval, and if f of a is positive, f of b is negative, or we could have reversed those, but we proved there's a 0. Well, in calculus, we tend to just extend this just a little bit, and we say this. We say if a function is continuous on ab, okay, so I'm going to repeat that top part. Okay, so do this fast. If a function is continuous on the interval ab, now it is possible in the test they'll say differentiable, but differentiability implies continuity, so that's fine. Because differentiability they may say that to try to, they don't want to tip their hat that it's mean value theorem, so they still may say differentiability here. So if a function is continuous on AB, okay, then here is going to be our then statement. Then, and this is going to be a little bit slang, then all x values in this interval, a is less than x is less than b, okay, have corresponding y values f of x that are between f of a and f of b. Okay. Now, there's a reason why I didn't use an inequality statement here, because it all depends whether your function's increasing or decreasing, which is why on this example up here, if this function would have been going the other way, f of a would have been the negative, and f of b would have been the positive. That part doesn't matter. You can flip-flop those. It's still confirmed by the intermediate value theorem. But down here it's a little bit different. I'm not talking about proving a zero. I'm just proving that a value exists in the interval. So here's the picture difference here. So if here is my picture here, same basic idea with my function here. Okay, so there is my continuous function. But notice the difference of my interval. Now, f of a is positive, but that really didn't matter, and f of b is also positive. Okay, so now I want to read this a little bit closer. So if a function is continuous on the closed interval a to b, it is, then all the x values between a and b, so every x value in here, okay, every x value in here has a corresponding y value, okay, corresponding y value that I'll call f of x or y value, that's between f of a and f of b. That's the intermediate value theorem. So here's what they usually do in a problem. These are very popular with table of value problems. And so it'll be a table of value question, and they'll tell you in the problem that the function is continuous. And I'm just going to make this up. Here's what they'll do. Maybe this is a time, and this is a velocity. Okay, it'll be something like that. And this will be 0, 2, 4, and 10. And this will be the velocity at 2 is 15 feet per second. Let's say this is 35 feet per second, and at 10, this will be a simple one where it just keeps increasing here, and it's at 70. So this would be the kind of problem they'd give you, and they would say, prove that there's a value that at some time, the velocity is 45. Okay, so it'd say prove that at some time v of t is equal to 45. Okay, and you'd look at that and you'd say, well, yeah, of course it's got to be, because they tell you in the problem that the velocity is continuous, and you're looking at this going, well, it goes 0, 15, 35, and 70. Well, of course it's got to be 45, because at my two extremes it's 0 and 70. Or they might say, prove, more precisely, they'd say, prove v of t equals 45 somewhere in this interval. That'd be what they'd say, in the interval 4 to 10. And you would say, oh, well, at 4 I get 35, and at 10 I get 70, therefore, by the intermediate value theorem, sometime in this interval I have to cross 45. It would be something like that. Okay? That's the intermediate value theorem, proving values exist in an interval. Okay? Now, mean value theorem, if a function is continuous on AB and differentiable on the open interval AB, then here is what's true. Well, first let's draw the picture. This one goes kind of more to classic calculus questions. So here's y, and here's x. Okay, and so here is a, and here is b. And so there is my f of a value. And there is my f of b value. So if a function is continuous on the closed interval and differentiable on a to b, then here's what we know. Then we know that the slope of the secant going through those 2 points, whatever that slope is, there is a value in the interval such that the slope of the tangent And so I'm going to say maybe that's about right there. The slope of the tangent is equivalent. That's what we're proving. So really what we're saying is, they're saying the slope of the secant, which by the way is equal to the average rate of change, is equal to algebra 1 slope. So we would say f of b minus f of a all over b minus a, okay, is equal to the derivative, that there is a c value. I didn't put my c value down here. There's a c value in the interval such that the derivative is equal to c, and that would be I rock, which is equal to the slope of the tangent. Now I'm putting these extra things on here. Okay, this is the guts of the mean value theorem. So if a function is continuous on a to b and differentiable, then I got to make sure I stress this to you guys. Then this box is what's true. Then this is true. So frequently, with the tip that you're going to be doing this is you're going to notice that there's a difference in the functions. There's going to be something about the average rate of change or the original function, and you're supposed to prove that its average rate of change is equal to the derivative. So notice there'll be a difference in the levels, we call it. This was all about f. This one's about contrasting f with f prime. So frequently what they'll do is they'll say something, for example, they will say, prove in an interval, it'll say something that f prime of 2, or sorry, f prime of x was equal to 4. Okay, prove that there's some time in the interval, and let's say this would be in, and I'll just say 0 less than or equal to x less than or equal to 8. Okay, there'll be some interval that you'll have to prove that this is true. Well, then all you have to do is do this. So this is what it'll say. Show some time in the interval that that's true. So the way you prove it is this. You do f of 8 minus f of 0 all over 8 minus 0. Okay? Now, if this equals 4, if that equaled 4, you just showed it. And usually that's how they're kind of set up problems. Okay, so make sure you can read that there. Okay, and where I got the 8 and the 0 was right here from my example. So in the context of a question, whatever they're talking about, you'll see this part that says, prove that this is true. And you'll just go, oh, well, I just have to go the original function at the interval they gave me. And I just have to find the average rate of change. And it's almost always going to line up. I don't know if I've ever seen one where this didn't work and you say, therefore it's not true. It's almost always true. So all they're trying to say is, they're having you prove the instantaneous rate of change, and you demonstrate the average rate of change. So if it's by the mean value theorem, they have to give you one of these, and they almost always give you the derivative, and you just do this. Okay? So as you contrast the questions as you're reviewing, go through the FRQs, and just look at all the ones where it says mean value theorem, and you'll start to notice this pattern. Okay? So that's the contrast to two. Hope that's helping as you prepare, and we will see you next time. Thanks for watching.